Hey everybody, Tim Brzezinski here. In this screencast, we are going to reconstruct this Toblerone in GeoGebra 3D, and we're going to explore an augmented reality at the very end. But we're going to do it in a way very different from yesterday, but we're going to do it through using functions and function transformations. I'm talking more like maybe Algebra 2 pre-calc kind of stuff, maybe some Algebra 1, we'll see. But check out this Toblerone. We know it's a triangular prism. Base is an equilateral triangle, right? That's why us math teachers love it so much. But take out two of the lateral faces kind of look like this, right? So I'm going to put this right over that, and there's the Toblerone right there. But let's just drop this for a second. When you're graphing functions, can you tell me what function looks like this right here? It's like an upside down V. And if you said absolute value, you're absolutely right. We are going to build this Toblerone in GeoGebra 3D, this time not using the prism tools or anything like more of the geometry tools. We're going to approach it more algebraically. We are going to build using functions, and we're going to transform the absolute value functions. So let's rock and roll. I'm going to share my screen, and we shall go. So here we are. Now, I have the absolute value function drawn right here. All right. So there it is here. But notice here we have the z-axis. Here's the x-axis, right? So z is equal to the absolute value of x here. When you work in 3 dimensions, z is the dependent variable, no longer y. Okay, that's first rule of thumb you gotta get across. Second thing is that both x and y are independent variables, right? And some of you know what I'm talking about. Some of you are like, well, what do you mean? I'll show you what I mean here. You see this, when you look at it this way, you're only seeing a limited perspective, right? Yes, we see the absolute value function on both screens, but the world in which we live, ladies and gentlemen, is 3-dimensional. So why we math teachers actually stick to only the 2D coordinate plane is beyond me. If we live in a 3D world, why aren't our students modeling and building in 3D more? Oh, so that's just one limited perspective, but you want to see the real thing. Here you go, right? That black absolute value graph is literally a cross section. Actually, the z equals absolute x is not the black graph. It is actually the red surface. That's first thing, because z is here, x is here, the y-axis is right here, perpendicular to both of them. But the point is, it doesn't matter what y is. Y isn't even a part of this equation here. So when we look at this in 2D, it's actually a subset of a 3D, like this, if you will, right? But many students don't really look at it that way, but we need to see it that way more. So here's the Toblerone right here, right? And if I may, let me just get this up and running here. Just want to mirror my phone here for a second, just so I can get this across here. There we go. All right, so let's do that. Let's go to the camera here, put it right there. So when we're looking at this, right, notice how we have to take that, thing, we have to take that surface you see right there on the right, and we have to kind of make it look like this. So what would we do to that V on the left to make the V on the right? And most of you know, just make the coefficient of the equation negative, right? That is a great start. So let's do just that now. Okay, let me turn this AirPlay off, and we'll do that. Oh, there we go. Goodbye. All right, so now let's actually go here and see it just the way it is, right? That z equals absolute x. Let me just hide this all together. So if you said if I make this negative, right, then, oh, that's a good start, right? You see the same function transformations kids are working with in 2D, they can do so and work with in 3D. Let's let them, okay? Now, let's actually go here now. Because in the 3D calculator, GeoGebra, right, if I just simply type in absolute value of x, I get the graph, but I have to actually put a 0y in there because I need to tell GeoGebra, hey, I'm going to graph a surface function now of 2 variables, and that's what I get, literally right there. Okay, now because, let me go to this screen right here. Because that edge there is 3.5 long, well, let me make it negative first in front. Let's flip it. So that's good, right? And I want to bump it up a little bit. But the question is, how high up do I go? Do I go up to 2, to 3, to 4? And I got to shave it off a little bit too. So Tim, how am I going to do that? We're going to answer that question now by going here. Let's take a look at a big hint. That is a cross section right there of, again, the absolute value function there and there. It has the dimensions. I'll put in there for you. Okay, let me get my phone back up and running here. And we'll put that right there. Just to see it again. Okay. And there's that absolute, I don't want to get too close there. There's that absolute value function right there. Let me put it more over here. That's better. Okay. So That blue triangle is really that yellow triangle right here. See how the edge is 3.5? Edge is 3.5. So what can you tell me about the makeup of that equilateral triangle? So the question, I guess the question I want to know here is how high up? Let me see if I can do this effectively here. Never done this before with just 2 hands, but put it right down there, right? So there it is. Try to keep it right there. How high up do I mean, where is this? What's the coordinates up here? I mean, this is like 1 point something, right? Well, yeah, half of 3.5 is 1.75. In fact, here's the hint. Whoop, right? 1 3/4, 1 3/4. And oh my goodness, you know, hopefully we don't tell students this, but I'm just trying to speed up the screencast. But we have a 30, 60, 90 triangle on the right side, don't we? Whose shorter leg is always half the hypotenuse. And so therefore, what's the value of that question mark right there? Now, some of you are jumping out of your seat saying, oh, it's 1 3/4 times the square root of 3. And some of you are like, you don't need those rules. Just do the Pythagorean theorem. You get the same thing. You're absolutely right. Now, just to play around here, I'm thinking, well, you know, it's probably going to be somewhere around maybe 3 point something-ish. But, oh, wait, I got to make that thing negative, don't I? That m, you know, kind of stands for slope. But what should that coefficient in front be? Should it be negative 1.5? Nah, too wide. The goal is to get that cross-section equilateral. Now we're getting pretty close, looking good. Oh, too much. You see what I'm saying? But what do we do now? What is this value right here? Now, if you were to solve for it, your students solve for it algebraically, it is 1 3/4 times the square root of 3. Or, you know what, throw out the simplifying radicals altogether. Just get what you get and throw it in there, right? The exact value. Simple radical form is irrelevant. It's not necessary today. Okay, so looking at it this way here, all right, I can see, let me go back to my 3D calculator here. I'm thinking to myself, you know what? We know that that's got to be, shut this off so I bandwidth here. Give me a second. Stop mirroring. All right. So we know we got to think about plus, right? 1.1 3/4 times the square root of 3. The keyboard's down here. So square root 3. All right, so that's what that z-intercept is right there, right? If that makes sense. Okay, but now this coefficient in front has to change, right? That scale factor, that m we had there, which was really the absolute value of the slope of both lines. So if we go here, what's the ratio of this divided by this? Well, it'd be 1 3/4 root 3 divided by 1 3/4, which is just the plain old negative root 3. Negative root 3 is actually roughly 1 and negative 1 and 73/100ths, right? So I'm going to go here just to save time. But again, I don't force students to put it in simple radical form. They can just type in the exact coefficient, divide exact value over the exact value, 1.75, right? But negative square root 3, get it up here. Negative square root 3 times the absolute value of x. Again, the 0 y just has to be there to make it a long sheet. So it's 1.75 times root 3. Now, would you look at that? Does that look like it's equilateral now? And I would say, look at that. That looks pretty good, I think, right? So let's actually, but now we have to throw a domain restriction in here. I can say that, and just to save time, we did this yesterday. Think of the bounds here, right? Isn't negative 1 3/4 is less than x less than 1 3/4 here, right? See how you can actually restrict the domain by just putting commas in there? All right, and also, since the prism height, it says here is 21, I could say 0 less than y less than 21. Okay, and then enter. Now, it actually GeoGebra rewrites the whole surface itself, but let me actually make the font smaller so you could see it better. All right, but here, settings, yeah, the ginormous 32. Let's fit it in better, 20. Okay. So there it is right there. But let's actually see how negative root 3 is like the quote unquote slope, if you will. And there's the z-intercept right there. So if we go back here and think, okay, kind of like going zoom out a little bit, zoom out. All right, looking like it sort of thing. I know it seems chopped off. That's just a pixelated app thing. You know, there's nothing to worry about there. Okay, we're good. All right, and now how do we actually put in the how could we actually take time to put in the other plane? Well, some of you are saying, well, that's just z = 0, isn't it? And you're absolutely right. That's z. There it is. So we could say here z equals or just put 0x plus 0y. That's even better. That's the floor. And now I could say, hey, negative 1 3/4 is less than x, less than 1 3/4, right? And then 0, comma 0 to y to 21. There is the base. Boom. That's it. So I'm going to take this and this. I'm going to right click, go to settings. I'm going to hide their labels. And there's my Toblerone, if you will. All right. Now, I could take this. I could right click. I can hide the plane. I can hide the axes. And that's kind of what it looks like. Does that look equilateral to you? Looks equilateral to me. But let's actually take a look at this in AR and see for ourselves here. All right. One little 3D trick here. So if you right click in the space and go to settings, if you make the clipping box size large, it actually shows more of it. Like you have a wider viewing window, if you will. You know, I'm not sure why it kind of chops pieces of it off, but we did type it in correctly. Totally. We did. But right here, for example, like there, and so I can move it over by hitting shift and going up and down. But that's it. Okay. But now let's take a look at this in AR. So what you normally do is go to File, hit Save, and I'll just call it Untitled or whatever. It doesn't matter. But if I hit Save, it'll save it to my GeoGebra page, my GeoGebra profile as a construction, if you will. And notice here the URL here, JBR, blah, blah, blah. If I were to type that in on my phone, which I'm going to open right now, I would get it. But because I want to keep the screencast short, I'm actually going to show you quickly the same version of this. I made this exact thing like an hour ago. And this is what it looks like, okay, when you put it to the test. So that's that. We'll go down here. We'll put this up here. And now here's the equilateral triangle that we had before. All right. And let's check it out. So we'll go to a 3D graphing calculator. There's, I made them different colors too, but there it is. All right. See how it's the same, same equation right there? There's the floor. There's the, there's the function that we used, right? And so now I hit the AR button right there, and I could actually show it off in the real world around me. So here you have it, ladies and gentlemen, here you have it, ladies and gentlemen, a Toblerone bar that was built by taking an absolute value function and transforming it. That's how we got two of those lateral faces right there. And if we want to, we can actually take a peek inside, right? Definitely looks equilateral. Let's actually test it this way first. Let me hold it over here. Hang on. So here's the absolute value function. Let me hide the floor. Book bag there. I should clean my office once in a while. So go here, check it out. Here's the Toblerone, and there's the cross section. Pretty good fit, I think. But now let's actually put it on the desk and superimpose this absolute value surface on top of it and see how well it fits. You can actually hide that. And wait for it. Boom. And there you have it. Toblerone bar built by taking a function that students always work with in an Algebra 2 or pre-calculus, even Algebra 1 class, right? An absolute value function used to model two faces of a Toblerone. And the other face equation was pretty easy to author right there. That is the power of working with GeoGebra 3D and augmented reality. You could have students build real-world models because we live in a 3D world. But not only that, you could have augmented reality allows you to test those models that the students actually make. So that's what I wanted to show you here. I hope you liked it. And if you choose to do something like this with your students, I would love to hear from you. You can find me at Twitter at @dynamic_math. You can subscribe to the channel, put some comments in here. I look at them every once in a while, but I would love to hear from you. If you like what you see, feel free to subscribe below. Thanks for watching, and hope you have a great Tuesday. Bye-bye.